Jiaji and Hui at Swinburne. So the overview of my talk today, essentially I want to start with just a fairly gentle introduction to how we do the experiments in strongly interacting Fermi gases, so using Bragg spectroscopy to probe Fermi gases. I'll then spend a little bit of time discussing the similarities and differences between phonon and single particle excitations, because we can see both of these in our system. And then I'll go on to describe how we can quantitatively determine both the speed of sound and the pairing gap from the Bragg spectra that we measure. And we can do this across the BCS-BEC crossover. All right, so the system that we use is a gas of spin-up, spin-down fermions in a mixture of the lowest two hyperfine states in lithium-6. And this allows us to take advantage of the broad Feshbach resonance that exists at 832 Gauss in this system. So this, we've already heard talks this morning from Christoph and Selim, who've been using exactly the same system. So for our experiments, we're using a three-dimensional gas, and the typical temperatures that we use for our system is about 0.1 of the Fermi temperature. So this lies below the superfluid transition temperature at unitarity. And typically we have something like 300,000 atoms per spin state in the gases that we use. So the way we do the experiments is shown schematically in this simple picture here. So the idea is that we take two tightly focused Bragg beams. We focus them down such that they intersect in the center of our atom cloud, as shown here. By appropriately selecting the frequency and the wave vector of these two laser beams, we get an interference pattern that moves with a speed given by omega upon k, where omega is the difference between the two laser frequencies, and k is just, or this little k here is just the magnitude of the wave vector. So in this condition, we can, with this simple setup, we can think about Bragg scattering of single particles, so we can have a single atom that simply Bragg diffracts from this periodic potential. And just by conservation of energy and conservation of momentum arguments, this Bragg resonance condition is shown here. So it's set by k squared here, where k is this wave vector of the interference pattern, and you can see that by tuning the angle to be either large or small, we can make the momentum range that we probe either large or small. So here we've got a relatively small intersection angle of 13 degrees, which means we're going to be probing long wavelength excitations in the cloud. The other feature of our experiments is that by focusing the Bragg lasers into the center of the cloud, we effectively probe a region where the density is nearly homogeneous. So we can calculate the density n bar. This is given by essentially an intensity-weighted measure of the density in the volume which the Bragg lasers probe. And the density is important here because it sets the energy scale of relevance for the gas, the system that we're looking at here. So we can get fairly close to a homogeneous system. So the typical mean density averaged over this volume that we probe is usually well within 10% of the peak density. So we're really looking at a fairly homogeneous flat density profile in the middle. All right, so now I'll talk a little bit about what we expect to see. So in the slide I showed you before, we talked about the Bragg condition for single atoms, and that's just simply a quadratically dispersing relation. In the strongly interacting regime, we can look at the calculated excitation spectra. So this is something that's been looked at for a number of years now, over the past decade or a bit more, by a number of significant authors. And the essential essence of what we expect to see is shown in this slide here. So first of all, at low energy, there's this strong mode, which is the Bogoliubov-Anderson or Phonon mode. And this is actually a Goldstone mode. So this comes about due to the spontaneous symmetry breaking that occurs when we produce a superfluid in this system. So this is a gapless excitation with linear dispersion and vanishing energy in the long wavelength limit. So this is something that hasn't yet been observed in Fermi gases. But if we increase the energy up to, and this is, I should emphasize, this is the only excitation that exists at low energy in these systems. If, however, we increase the energy that we probe the system with, then we can eventually cross this threshold here, indicated by the blue line, and this corresponds to 2 delta, or twice the pairing gap of this system. So when we've got a Bragg energy that's greater than 2 delta, we can break apart a pair, provide enough energy to essentially remove 2 atoms from a pair and excite them into the continuum. And so above here, we should get these pair breaking or single particle excitations. So this is shown at unitarity. This is kind of a schematic picture, but to set the energy scale, the pairing gap here, or twice the pairing gap, is of order the Fermi energy, and this dispersion stays linear over the range probably from about 0 up to about the Fermi energy, the Fermi wave vector, sorry. All right, and in the experiments I'll talk to you about today, this is the range that we're going to be probing. Okay, so what do we do when we do our experiments? Well, this slide shows the basic picture. So we apply our Bragg pulse to a trapped cloud. We then turn the trap off and let the cloud expand for some time, and then we take a picture of the cloud and work out the centre of mass displacement. And this centre of mass displacement is proportional to the change in momentum, or the momentum that we've imparted to the cloud. Okay, so this picture on the right here shows a typical experimental image. What it's actually an image of, though, is the image of a Bragg scattered cloud minus the image of a cloud without any Bragg pulses applied. So what you can see here is this blue region indicates where we've removed atoms, and the red region is the atoms that have moved away after some time of flight. So to get quantitative information out of this image, we can simply integrate over this region, obtain a line profile, and calculate the first moment from that. That gives us the centre of mass displacement, and then we can get a number that's proportional to the momentum we've transferred. In linear response theory, this momentum that we transferred is just proportional to the imaginary part of the density response function, chi of k omega, and where this chi of k omega is given by the Fourier transform of the retarded density correlation function in the usual linear response theory. All right, so to show you now what we actually see when we do the measurements, this slide actually contains all of or essentially all of the spectra we measure, but there's a lot of things, a lot of detail to cover in here, so I'll spend a few minutes going through it. So if these plots here are measurements of the centre of mass displacement, or the momentum transferred, as a function of the Bragg frequency omega along this axis for different interaction strengths. Okay, so if we look in the BCS limit over here in the far right-hand side, what we see is a fairly broad response indicated in this red curve over here. And this gas here is actually quite weakly interacting. So it's got a 1 upon KFA in the minus 1.6. So this is well in the BCS regime. And for the temperatures that we use in our experiments, 0.1 of the Fermi temperature, this lies well above the superfluid transition temperature. So here we're just seeing single particle excitations from a weakly attractive Fermi gas, or weakly attractive Fermi liquid. Then, as we start to increase the strength of the interactions, moving closer to the Feshbach resonance, we see a new feature appear in our Bragg spectra. So these red features or these red data points indicate single particle excitations, but as we go closer to the Feshbach resonance, we see this new feature emerge in the Bragg spectra. Sorry, and that's actually the Bogoliubov-Anderson Phonon mode, or the Goldstone mode here. So we first noticed the appearance of this feature at around about 1 on KFA of minus 0.5. So this is still in the BCS limit, but for the temperature that we have in our cloud, the temperature of our systems, about 0.1 of the Fermi temperature, this is approximately where we expect to cross the superfluid transition. So the appearance of this mode is corresponding to where we expect to cross the superfluid transition, as well as within the error bars that we can do our thermometry out here. And then we see this phonon mode grow to become the absolutely dominant feature in the spectrum. So this is really a very strong feature in our Bragg spectrum. It grows in amplitude as we go further and further into the BEC side. So one of the other features that you'll notice here is that this red branch, the single particle excitations, do two interesting things. Firstly, they drop off in amplitude, eventually becoming impossible to see once we cross onto the BEC side of the Feshbach resonance. So this is for the particular momentum we're using, about 0.5 of the Fermi wave vector, or Fermi momentum. But also you'll notice that this branch, excitation branch, separates out from the collective mode. And this is actually the direct appearance of the pairing gap in this system. So we can really take these spectra and directly measure the pairing gap in the region where the two excitation branches separate out. So this is really, we would only be able to do this by taking advantage of this focused beam Bragg spectroscopy that we use that allows us to measure the response from a region of fairly uniform density. So we're not integrating over a range of different densities here. Okay, so now I might just spend a couple of minutes giving a sort of cartoon picture of the two different types of excitations that we see, because they're actually quite distinct, or we can think of them as distinct physical processes. So in the single particle regime, essentially what we think of is that single particles just come in and Bragg reflect off a moving lattice. So if we think about what's happening in the frame of the lattice being stationary, we have a single atom coming in here, interacting with this periodic potential, and then just reflecting off by flipping the sign of its velocity. So in single particle Bragg scattering, what we have, if the lattice moves with the speed of omega upon k, the single particles recoil with the speed of 2 omega upon k, if they were initially stationary. In the phonon regime, or the phonon scattering, is a little bit different. And what happens in the phonon picture is essentially where the Bragg lattice is moving slow enough that the atoms respond collectively to the system. So instead of knocking out single particles, we basically just perturb the density, or we create a disturbance in the density distribution, and that propagates along here at the speed of sound. And so we can resonantly excite this mode when the velocity of the lattice is equal to the speed of sound in the gas. So this is, so here there's many, the Bragg laser, there's many atoms involved in producing this excitation. Here there's only a single atom involved in the excitation. So what does that look like? Or that actually leads to some qualitatively different features when we perform the experiment. So if we look at the single particle scattering first, that should be the easiest to understand, and it turns out that it is. So if we take somewhere on the BCS side of the Feshbach resonance, and we tune our Bragg lasers to this point up here, so well above the threshold for producing single particle excitations, 2 delta, which is shown by this red line here, then we can excite, then we just expect to excite single particles. And when we look at the image after the Bragg pulse as a function of time of flight, this is exactly what we see. So we basically produce a hole in the center of the cloud, and we get these atoms moving off towards the right at the velocity that I mentioned. So they're moving with twice the recoil velocity, or moving at twice the velocity of the lattice. The recoil velocity is twice the velocity of the lattice. In the phonon case, it's actually a little bit different. So let's say if we go to the BEC side of the Feshbach resonance, we produce an excitation here on the dispersion relation. I should mention that the single particle continuum here is way up off the scale of this graph, so it doesn't actually come into play. Then what happens as that excitation begins to propagate? So we think of that as a sound wave. It moves out from the center of the cloud into regions with lower density. So the situation is going to be something like this. So we're going to go from a region, this is where we excited it, but then once it propagates a bit, it's going to find itself in a region where the dispersion no longer, or where it no longer sits on this dispersion. So the only way that we can conserve both energy and momentum in this case is for this phonon to decay. So it decays down to lower, or to longer wavelength, lower energy excitations in a mechanism very similar to Belayev damping that's been studied previously in a range of systems, including atomic BECs. Then eventually this propagates out then eventually the density becomes so low that this will evolve into single particle excitations. But what we see in the time of flight images, if we look at this, is a little bit more complex. So there's clearly some interesting dynamics here. So for short times of flight, we see that there's some modulation and dynamics happening here, and then eventually, once we get to lower density, we see the appearance of this longer wavelength structure in our images, which seems to propagate out, where the minimum that we produce tends to stick fairly well close to the maximum. I should also say that the wavelength of these features is much larger, almost a factor of 10 larger than the wavelength of the Bragg lattice that we use to excite the excitation initially. So there's obviously some interesting dynamics in the decay of this phonon, but that's a topic that we plan to investigate in the future. So now I'll spend a few minutes talking about or looking in more detail at the Bragg spectra that we have, because we can learn some, or we can get some accurate quantitative information from these. So if we look specifically at the Bragg spectrum at unitarity here, we can see, well, we've got this very strong feature here, the collective mode or the Goldstone mode, which dominates the response. But then at higher energies, we see this bump that happens out here, just below the energy of the Fermi energy. And so this point is the point where we start to produce single particle excitations. And we associate with that, we take the point 2 delta to lie halfway between this upper point and the lower point, and from that we can get a measure of the pairing gap in the system here. So our measure when we plot the spectra in units normalized to the Fermi energy, we find a pairing gap of 0.47 of the Fermi energy, which is in good agreement with previous measurements and theory. I'll show a comparison in a couple of slides' time. The theory curve here, this dashed line, is a random phase approximation calculation that was performed by our collaborators Jami Kanunen and Georg Brun. I won't talk too much about that in the interest of time. So we also see both single particle and the collective mode at different regions, or in a range of for a range of interaction strengths across the crossover. And when we do see that, we can essentially just read off the pairing gap as a function of the interaction strength. So here we've plotted the Bragg spectra from unitarity here onto the BCS side. And as we go down with interactions, so here at about minus 0.1, we can see the gap is starting to shift closer towards the collective mode frequency. At minus 0.2, it's almost merged. And then down at about 0.4, we no longer resolve the pairing gap. It's going to lie here somewhere. So the collective mode and the single particle excitations have merged at this point. So we can use this to plot or to measure the gap. And so we've plotted those 3 points here. And I've just listed up here a table for comparison of previous theoretical work that's calculated the gap, and also the previous RF spectroscopy experiments that were performed at MIT in 2008. So our number agrees quite well with the earlier measurements and also these theoretical predictions. We could do a bit better on the error bar here if we really work a bit harder to or take data with a little bit finer resolution around the point where the single particle excitations start. And that's something we intend to do in the future. The error bar at the moment is limited by that factor, and also by the fact that the uniform, or the density, is not entirely uniform. So there's kind of a little bit of spreading because of that as well. The other thing with Bragg spectroscopy, that doing it in this way, it's a little bit simpler because we don't have to take account of final state effects, because we're not changing the internal state of the atoms. And also the Hartree energy doesn't come into, or the Hartree shifts don't come into the measurement in this way. So the other thing that we can take from our Bragg spectra is that we can look at the position of the collective mode, and provided we're in the linearly dispersing part of the dispersion relation, then this tells us directly the speed of sound. So we can measure the speed of sound by simply fitting. So what we do is we fit to find the center frequency of the collective mode, the Bogle-Bob Anderson phonon mode peak in our Bragg spectra. And then it's simply that tells us where we are on the dispersion relation. So if we're linear, then omega divided by k is the speed of sound. So we can plot that normalized to the Fermi velocity here, that's shown on the right here. So our data are these blue points. There have been a number of previous studies of the speed of sound, and our data, I don't have them up here, but our data agree quite well with previous studies. And here's just a couple of theoretical calculations of the speed of sound. There are others that we will compare with as well, so apologies for not showing all of the theories here. But we see very good agreement in this range of interaction strength. So near unitarity is where the dispersion remains linear for the longest. As we go away from unitarity, then the dispersion starts to show some curvature. So on the BCS side, it curves downwards, which means we get an underestimate of the gradient. And on the BEC side, it tends to curve upwards, which means we get an overestimate of the speed of sound. So we can use our theoretical model shown or we can use theory to help us correct for this. So the theory developed by our collaborators in Finland and Denmark allows us to, or agrees very well with the dispersion that we see in this regime. And by taking the gap that we measure here, they can use that as an input parameter to their theory, and we can calculate the expected shift of the collective mode frequency if we were to look, or the expected chain error that we make when we try and determine the gradient up here. So we can correct for that. That's given by these open circles here. And these data actually, or seem to follow the theory curves quite well. And similarly, we can do the same thing down there. All right, so with that, that's basically all I wanted to talk to you about today. So the take-home message is that we can use this Bragg spectroscopy at low momentum to make very precise measurements of the properties of these strongly interacting Fermi gases. We can see quite clearly the Goldstone mode in the unitary Fermi superfluid and on the BEC and BCS sides of the Feshbach resonance. We also are able to measure the pairing gap and speed of sound, essentially directly reading off our Bragg spectra. And we also see this fairly complex dynamics happening here when we excite phonons in the system. So in the future, we want to look more closely at the temperature dependence of these Bragg spectra, particularly at the unitarity case, and understand the phonon dynamics that are happening here in the decay of the phonon. With that, I'd like to thank my team, so particularly Sasha, who was really driving these experiments. Also, Paul and Tyson are here. They've been working on the 2D Fermi gas experiments at Swinburne. They had a poster on Tuesday. And also Peter Hannaford, who's been supporting and helping our group for a long time now. So with that, thank you very much for your attention.
Thank you for the wonderful talk. Now the session is open to questions and comments.
Chris, very nice results, and it's wonderful to sort of see the different character of the modes. Thanks. I have a question about your finite momentum transfer. Yep. A momentum transfer of 0.5 kF is not necessarily small.
That's right.
So if you determine the gap by just visually looking at the gap of the spectrum, shouldn't you extrapolate to zero momentum transfer, or what is the role of momentum transfer in this determination?
I mean, perhaps I can put the dispersion. So at unitarity, it's certainly true that there could be some shifts, but well, it's actually a little hard to see on this picture here, but if you really look at this, so we're in this regime here, so the point where the collective mode merges with the single particle continuum happens, I should have put a label on this, sorry, but happens around, or we expect it to happen around about where k is equal to the Fermi wave vector. So, and at that point, the single particle branch certainly does curve upwards. I think this is what you're getting at, that somehow, because we're not measuring here, the pairing gap might be shifted a little bit. Is that what I understand your question is?
No, I was just wondering what would happen if you change the momentum transfer,
So
and to what extent do you have to correct your determination of the gap by just looking at the separation of the two features? Is there maybe a correction on the order of momentum transfer squared or something?
If there is, it's very small. Certainly the theory that we've looked at doesn't show anything here that would be big enough for us to detect experimentally. It looks essentially really flat across here, and this is what papers going back to the early work by Combesco and Stringari have shown as well in this regime. Certainly when you get close here, then you would see it. The other difficulty is that it's a little bit difficult to see from this picture, but the single particle branch also gets very heavily suppressed here as you go to lower and lower momentum, so it's harder and harder to excite it. So then at some point you have to worry about nonlinear processes as well. So we can see if we turn up the intensity too high, that this collective mode feature broadens so much that it actually starts to overlap here. So it's a trade-off between the intensity we use to do the measurement and keeping far enough separated from the collective mode feature.
Okay. Any other questions? Actually, I have a... No? Okay, I have questions. You mentioned about the high temperature study for searching for the pseudo gap.
Yep.
Which means having the phonon peak is assumed as a superfluidity.
Yes.
Okay.
I guess, so maybe to follow that up, you might ask the question, what would we expect to see in a spectrum if we took it and there was a pseudo gap present? I mean, actually, that's a good question. I don't know that anyone has a really good answer to that. But I think all of the theoretical calculations that people have looked at where they expect to see some sort of pseudo gap feature is that you might expect a kind of double bumped feature in the spectrum. So some sort of excitation at lower energy and then something that happens at higher energy. But the theory, I think it's very difficult to make an accurate theory of what you'd expect there. But yeah, I mean, that would be the sort of thing we'd be looking for, is if there's some sort of bump that happens at higher energy that we could associate with single particle excitations.
Thank you. Okay, if there's no questions, and then let's thank the speaker once again. Next, we have Professor Vanderlei Bagnato from University of São Paulo in Brazil.